Good morning to all, and I welcome you for the third day's first session. And the today's speaker is Dr. B. Chittibabu. He has received his PhD degree in electrical engineering from National Institute of Technology, Rourkela, India in 2012. He was an assistant professor in Department of Electrical Engineering, NIT Rourkela, India from 2007 to 2013. He had postdoctoral research appointments with the Wrocław University of Science and Technology, Poland during 2013-14 and with VSB Technical University of Ostrava, Czech Republic during 2014-2015. Both of these appointments were sponsored by European Commission UK. He was an assistant professor in the Faculty of Engineering, University of Nottingham, Malaysia campus, Malaysia from September 2016 to June 2018. Since June 2018, he has been assistant professor in Indian Institute of Information Technology, Design and Manufacturing, Kanchipuram, India. He was a visiting researcher at the Polytechnic University of Milan, Italy during 2015 and visiting scientist at Yildiz Technical University, Turkey during 2019. He was a recipient of prestigious Young Systems Scientist Award 2019 sponsored by Systems Society of India. Dr. B. Chittibabu serves as an editorial board member, associate editor of many peer-reviewed SCI Index journals, including IET Renewable Power Generation, IET Power Electronics, IET Energy Systems Integration, International Transaction on Electrical Energy Systems, Electrical Engineering Springer, Energy Sources Taylor and Francis, Energy and Environment Sage, and Automatica Taylor and Francis. He has published over 50 papers in SCA Scopus Index journals, including IEEE and IET. His current research interests include power electronic application, smart distribution grid containing renewable energy resources, design of low power photovoltaic system, including MPPT algorithm, control and grid integration of renewable energy systems. So we are all happy to have a speaker. And now I hand over the session to Dr. Chittibabu, sir. So now you can answer.
Okay, yeah, very good morning to one and all. First of all, I would like to thank, Chair Dr. Tangabulu, who has invited me to give an invited lecture for this proposed ACTA, Atal FTP program, and it's my pleasure, to give a talk on the area of advanced control strategies for grid integrated solar PV systems. Thank you for the, brief introduction about me, but still I'm a learner. So as I could develop the laboratory, what is called the Photovoltaic Research Laboratory at WTTM Kanchipuram, Chennai, with the DST, funding with the cost of around 40 lakhs. And we are able to develop the laboratory here for 1 kilowatts grid connected PV system and having networking with MNIT Jaipur and SVNIT Surat. So we have well established, the research in the area of control strategies for grid integrated solar PV systems. So and we have published a number of papers in good AC Index journal, including IEEE and IET as well. So that I wanted to share the investigation. So what was done by our the team. So I wanted to disseminate so that this may ignite the participants, so those who are doing research in the area of grid-tied solar PV system, so that it will get they will get a benefit out of it. And moreover, as the FTP is more relevant to the the electrical vehicle with the grid integration, and still the integrating electrical vehicle or integrating renewable energy like wind energy or photovoltaic, so still the concept it remains same, but maybe the control the strategies may differ, and also how the topologies, the power converter topologies are going to be, used to integrate such renewable energy or the electrical vehicle in with the utility grid. So that will be the concept. So the outline of presentation, including the objectives of the research and what you have done, and what is meant by grid integrated PV system. So how the system has been fabricated, and in the laboratory prototype, with a very low power and for investigating in the real time, and how the system architecture has been made, to make it this, small scale grid tied solar PV system, and how the control strategies has been implemented. As we have, investigated a variety of control algorithms with a very recent as well as the advanced control strategies. So how these techniques has been implemented in the real time with the help of the DSPs and in the laboratory prototype, that will be discussed here, and along with the experimental research what we have investigated in addition to the simulations, and that will be summarized with the references what we could be able to follow to find the problem definition. So that would be an outline of my presentation. So motivation. Yes, I mean, as we are all aware that there are two key technologies playing a very major role in the 21st century. Basically, the one is, the information and communication technology, and the second is the material science and renewable energy. So, of course, we should completely agree with my statement that the renewable energy is playing a very major role in the future. The energy systems, and moreover, and to mitigate the global warming and the greenhouse effect, even with this pandemic situation, that these energy systems are playing a very major role to have an green and clean power generation, and moreover, it also mitigates the CO2 emissions and greenhouse effect as well. So, such energy sources are basically an intermittent in nature, so that cannot be directly integrated with the utility grid, as you know. Basically, they are intermittent energy sources, or maybe the disposed power generation unit, and basically it depends on the, the input energy basically that we derived from the solar energy, So most of the energy what we extract from the sun, basically the energy like sun energy, basically a solar energy or the wind energy or maybe a tidal or maybe a hydro, so all are basically byproduct of solar energy, right? So it depends on the the climate, or depends on the seasonal the variation, so then output energy differs. So that is what I mean that. So the output power what we extracted from the renewable energy source like wind energy, as we extract the mechanical power from the wind turbine, and we extract the DC power from the PV array, and we extract the mechanical energy from the tidal or maybe wave energy, right? So the output power extracted from such energy sources, it largely depends on the input power, So let's talk about the photovoltaic, as you might be knowing that. So basically the input power, the input parameter which feed to the solar PV array, basically a photons, the solar energy, it has a two important, parameters or the variables, the temperature and irradiation. Okay, so the output power of the solar PV, it largely depends on the input power, the irradiation and temperature. So due to variation of irradiation and temperatures, and ultimately the output power is variable and uncontrollable, So due to this uncontrollable output power of the PV, that cannot be directly fed into the utility grid, and moreover, power what we extract from the PV is basically a DC power, right? So as the grid is basically an AC, and of course we need an energy conversion. We need the converter to convert that unregulated DC power into controllable AC power that can be fed into the utility grid. That is what. So the main motivation, besides this topic, the grid integrated PV system is basically to design and operation of power converters to achieve high efficiency for different power configurations. So that is what, maybe at a low irradiation or maybe at a high irradiation or with a different temperature components. So how we are able to extract the maximum possible power from the PV array, so that we are able to, feed into the utility grid with controllable voltage and frequency. That is what the key considerations in this grid integrated PV system. If you see, as we are going to design such a power converter, to have a controllable power with a high efficiency, of course, it needs certain requirements. Basically, that requirements are called grid connection requirements, or maybe the requirements for power converter. So that include maximum power extraction. As you might be knowing that extracting power from the PV is basically is it is as we are converting the low quality energy, what is called the solar energy, into electrical energy, the conversion efficiency is very low, as you might be knowing that. So so ultimately you have to invest a huge amount of money. Basically the capital investment is very high in the solar PV system, that the conversion efficiency is very low. Right now, with the developments in material science, with the multi-junction solar cell or the compound semiconductors, now the trend is getting changed slowly. Even there is a recent research is going on in the photovoltaic array. The formation basically called the bifacial solar cells. So instead of having solar cells on the particular the side, so they are fabricating the solar cell on either sides, so that is an excellent choice to extract maximum possible power in the very cold climatic weather like in Canada and even the western countries. So that configuration is one of the excellent choice. Still it is under research. That is what. So the maximum possible power extraction is an important requirement of a PV converter, as the conversion efficiency is very low in the solar PV system. And of course we need to feed power or controllable power with a high efficiency. And moreover, the power which is being injected into the utility grid is basically an active and reactive power that has to be a controllable one, because as the grid needs the constant voltage and the constant frequency AC power. Of course, so the constant voltage and constant frequency mean in turn it needs active and reactive power. As you might be knowing, active power control is basically a frequency control, and reactive power control is basically a voltage control, as it needs to have an independent power control that is being injected into the utility grid. And of course, while you're injecting an AC power into the utility grid, so the grid current must have a lower harmonic distortion. So that is one of the great challenge while you're integrating a renewable energy with the utility grid, because basically the power converter, it provides an asynchronous interface. So of course, and there may be the pulse width modulation and the switching, the switching strategy. So, and also due to non-linear load which is being connected at the point of common coupling, of course, there must be a distortion in the grid current. So the control technique which we propose in the power, the power converter is basically a grid side converter. So it has to, inject an AC power with a sinusoidal current injection. So that is one of the great challenges. And that is what, therefore, there must be a norms for power quality as well. And excellent transient response. The transient response is an important component in renewable power integration and that, because we generate power with the help of the static power source like a photovoltaic or maybe fuel cell or a micro turbine. They doesn't have any inertia, right? So whenever there is a disturbances, maybe it is externally or internally, it is very difficult to damp out such oscillations or the disturbances. So basically, that sources are the fragile power generating unit. Basically, they are zero inertia sources and that. So virtually, we have to provide an inertia to have an excellent transient response. That is one of the another challenge and requirements for the power converter. In addition to the grid synchronization, the grid synchronization is an important component. With the help of that grid synchronization, we are able to integrate such a renewable energy sources with the utility grid. So these are the possible requirements for the power converter. And to achieve these 6 requirements, and ultimately the performance of the converter connected to the grid depends on depends largely on the control strategy what we applies on the grid side converter. That is what. So the control strategy and what we apply on the grid side converter or grid connected power converter, yes, it needs to be precisely applied so that we are able to achieve these grid connection requirements. That is what variety of control techniques have been proposed in the literature, and to have a grid integration of renewable energy during steady state as well as transient condition. But still, it is not finding an exact solution for such energy sources in the countries like India, where we have very subtropical weather, having the temperature and irradiation variation is very wide, and moreover it is unpredictable. That is one of the another disadvantage of photovoltaic power generation system. So the forecasting of solar PV as well as the wind is quite difficult. That is what. So control strategy what we applies on the grid side converter, it's not straightforward. Of course, it has to be further investigated. That is what. So the objectives of my presentation, it includes the detailed design and development and implementation of grid interactive PV system, and a laboratory prototype. A 3-phase 4-legged inverter is designed and used here for the grid integration of PV system. And that proposed 3-phase 4-legged inverter is basically acting as a multifunctional inverter. So multifunctional inverter, it implies that, and it not only controls an active as well as reactive power injected into the utility grid, it also serves as an active power filter for power quality improvement. And hence, this is what is called the multifunctional inverter. So it performs, to satisfy all grid connection requirements. And for grid synchronization here, to have a precise control methodology, we have proposed an adaptive PLL-based synchronization scheme, to alleviate the effect of input signal magnitude and the overall system performance. As I told you that, the control method and what we propose on the grid side converter, it largely depends on the reference current generation. So whatever be the technique we propose, the control technique proposed on the grid side converter, so it has to be very precise and it has to be adaptive. So that depends on purely the reference current generation with the help of grid synchronization tool, what is called phase locked loop, right? So we propose to control the basically a fundamental parameters, such as the 50 Hz component in terms of active as well as the reactive power. So the PLL what we propose to estimate the fundamental component, that has to be adaptive in nature, and it has to estimate the fundamental frequency component very accurately. So by accurately estimating the fundamental frequency component, we are able to generate the unit vector generation called the sin theta and cos theta, so that we are able to implement such a sophisticated control technique of the grid side converter, so that we can have overall system performance. That is what. And in addition to that, the proposed system, it provides power quality improvement, because it is a very essential task in the power converter, grid interactive power converter. Because as you know that, I mean, most of the loads are basically non-linear in nature. So whenever a non-linear load which is being connected at the point of common coupling, of course there must be a grid current or source current distortion. So, and it causes a high, I mean, larger THD, and ultimately it affects other load which is being connected at the PCC. That is what. So to mitigate such a power quality, problems. So here the control technique, it also provide a power quality improvement, and moreover the load reactive current compensation whenever we connect a heavy inductive load at a point of common coupling. And moreover, we propose the three-phase four-legged inverter, right? So the four-legged inverter, it implies that for a three-phase system, usually we follows two-level, three-leg inverter for generating the three-phase AC supply, AC source with RYB. In addition to that, we have another leg, what is called fourth leg. So that fellow will take care of zero sequence harmonic compensation or neutral current compensation. So because it doesn't have any neutral current, it doesn't have any alternate current, alternate path for neutral current, and ultimately there is an existence of zero harmonic component, and hence there must be a third harmonic component. So you know, right? So as the order of the harmonics is very low, of course the severity is the problem. So that is what. So as we use as a fourth leg inverter, so that will provide a alternate path for the the neutral current, and hence there is no existence of third harmonic component. That is what here. And it also, it will take care of the neutral current compensation whenever an unbalanced load is connected at a PCC, like a three-phase diode bridge rectifier load or maybe adjustable speed drives. So it delivers an active power sharing feature based on the availability of active power at the DC bus terminal. So moreover, as the input power which is being given to that DC to DC boost converter is basically a PV. As we have a a DC source, what is called a photovoltaic. So it also contributes for power sharing to have an excellent energy management. So if you see that, as I told you that the main heart of the grid integrated PV system is a power converter. That is what is called a power electronics converter. So the power electronic converter, it provides an asynchronous interface between source and load, right? And if you could see that, the converter which was used during 1980s or 1990s, mainly, to improve the load dynamics in the industry, because most of the loads are adjustable speed drives, and it consumes around 60 to 70% of the total power consumption in the industry. So now what happened? Not only the loads need a good dynamic response, and the sources also intermittent. As I told you about, the sources are basically intermittent energy sources like a wind energy system or the photovoltaic. So ultimately, the converter needs to interface, the unregulated, the power source, like a renewable energy source, and also improve the load dynamics. So it provides an asynchronous interface with the help of controller. So it enables the technology to provide an asynchronous interface between two AC as well as DC electrical system. And the interconnection of two asynchronous AC system, it is possible with the help of power converter. And moreover, you need to have a DC to AC power conversion, because the the PV power source is basically a DC source. As the grid is a AC, so a DC to AC conversion is essential. That is possible with the help of power converter. And these are the listings of power electronic application. And in the today's scenario, that it is widely used in distributed generation. In all renewable energy sources like wind energy and photovoltaic and fuel cells and micro turbines. And we invariably uses power electronics. Even if you see that as an electrical engineer, we are very proud to use power electronics everywhere. That is what we carry the mobile phone. You know, the mobile phone, the power management ICs are working under the principle of power electronics. You know that. So the power density of the mobile phone basically depends on the battery, as it needs power conditioning unit. That is what the concept is from what is called the electronic power distribution system. So that is possible with the help of power electronics. And up to multi-megawatts, wind turbine system, we uses power electronics. And moreover, as the renewable power generation is going to be distributed, as it is basically, it provides a decentralized power generation unit, we invariably uses the storage unit. Okay, so storage unit especially to meet the peak power demand, and moreover to have a controllable active and reactive power, in addition to enhance the the grid stability, we use as a battery, supercapacitors and ultra capacitor and the superconducting magnetic energy storage, even the mechanical energy storage like a flywheel as well. Still we use as energy storage. So you cannot avoid energy storage in the today's power system, and hence the system is becoming decentralized power generation unit. So we need power electronics converters for power conditioning of all energy storage unit. And moreover, I told you that most of the loads basically, in the industries are adjustable speed drives, and even 95% we use as induction motor drive. And we should have a power electronics converters to improve the dynamic response as well as to meet the load requirements in the industry as well. We use as power electronics, and also there is a norms for power quality. As you might be knowing that today, 99% of the electronic loads are basically non-linear load, and there must be a problem of distorting the supply current. So then we should use power electronics converter to mitigate power quality problem. That is what we use as a dual feeders, uninterrupted power supply, UPS for the critical load, and in addition we use as a dynamic voltage restorer and a dynamic DVR and the STATCOM as well. So of course there is a problem for power quality issues, so we uses these custom power devices. And addition to that, still we use power electronics in the transmission and distribution side, as you might be knowing that. And we cannot avoid HVDC transmission in today's situation, especially for underwater DC power transmission. Still in the European countries they use HVDC transmission, even to have a long distance transmission between the two nationalities, two countries like Malaysia and Thailand, and they have a HVDC transmission. So even for medium voltage DC transmission in the the underwater cable, we use HVDC transmission. Of course, in Tamil Nadu, there is a HVDC underwater DC transmission between Madurai and Kandy of Sri Lanka. So that we use as a HVDC power electronics converters. And moreover, still we use the FACS devices called the flexible AC transmission system devices like a series and shunt compensation, even having compatibility of both the shunt and the series compensation, what is called the UPFC. We use in the power transmission system to enhance the system stability. And of course, we use shunt compensation to improve the voltage profile at the point of common coupling, and we use series compensation to enhance the system stability. Invariably, we use power electronics. You cannot deny. See, no power electronics, no modern power system. Of course, no modern power system. No, solid state control of electrical power. Of course, you need to have a very bulk electrical equipment like a transformers with the tap changes and the rheostatic controller, or maybe saturable reactor. So that scenario has gone. So today we are in the 21st century. Invariably we use power electronics converters. That is what. And still, even you use such a power converter, basically they provide a solid state control to have an flexible control mechanism with enhanced efficiency. Still we faces challenges in the today's power system. And what may be the challenge? As I told you, the complexity of traditional power system. You can see that there must be a strong coupled dynamics between generation unit, distribution, transmission, and delivery. So if any changes on the supply frequency at the generating station, and of course it causes, the variation of the speed of induction motor drive and the delivery. That is what. So it has, it has a strong coupled dynamics between the generation unit, distribution unit, and delivery unit. We need a decoupled control mechanism. So you wanted to have an independent control mechanism. That is what, if you see that in the industry, even whatever be the changes on the supply frequency due to variation of the the turbine speed, still you can control the frequency and the supply end by having the vector control of induction motor drive. Maybe you might be aware of that. So the problem is still we can't find very accurate solution for fully decoupled dynamics of generation, distribution, and delivery. Why? Not in addition to the existing conventional power generating unit, we are also integrating renewable energy sources like wind turbine and solar power and tidal and wave energy. So the characteristics of the renewable energy sources are totally different from conventional power generation unit. So of course there is a problem in complexity in control mechanism. So you know, right, the basically the electrical generation unit basically complex in nature, electrically, thermally, and mechanically. Basically it is a multivariable AC system. You know, it has a large number of parameters, and moreover it is, as far as the control system concept is concerned, basically it is higher order system. So very difficult to linearize the parameters. So there must be a complexity in control of the traditional power system in addition to renewable energy. And moreover, existing power generation unit like a thermal and hydro, basically they have an excellent dynamic response because of the inertia given by the turbine. So there, whenever there is a, the disturbances or disturbance occurs in the transmission line, still you can damp out the oscillation by having a solid state regulator on the excitation system, as well as you can have a governor mechanism on the turbine, so that we are able to damp out the oscillation because of the machine inertia. But today, if we could see that the renewable energy sources like photovoltaic and fuel cell, they doesn't have inertia. Basically, they're the fragile energy sources. So due to inertia-less system, very difficult to damp out the oscillation. Basically, the dynamic response is very poor. As I could read in the literature that if there is a 10% changes in the, sudden change in the load, if it is a fuel cell power source we are using to feed power to the load, for 10% changes in the load, ultimately it takes 1 to 2 minutes to reach the steady state. So you can see, you can understand you can understand the robustness of the, the control mechanism and the fuel cell, very poor dynamics. That is what the another, a problem we faces in the today's power system. Of course, we need to have a such control mechanism to linearize all the parameters. So there must be an independent controller, decoupled control between and voltage and frequency in the grid. That is what the important solution with this today's situation. And moreover, local focus of power electronics. As I told you that even during 1980s or 1970s, we concentrated only on load dynamics, and we use as the induction motor drive in the industry. Basically, they are adjustable speed drive. Now the scenario has gone, because not 50% of the energy is consumed by the industry, in addition to the 30% of the energy consumed by lighting mechanism on the building. So you can see that the lighting, how the the evolution has come into picture in the lighting. We use as a LED and LCD lighting, and still we face the problem of power quality as well. So we have to focus both on load dynamics as well as source dynamics. That is what the evolving focus of source dynamics, UPS, distributed generation, and alternative energy sources. Until now, only fixing the problem of power distribution is happened. So we have to find the correct solution to mitigate such problem, and still it is a challenge. So what will be the challenge? Whatever you use the power converter or power electronics for, having very dedicated control mechanism to have an excellent dynamic response, the finding the solution in a cost-effective manner is very difficult. Of course, we have to have a very expensive power electronics converters between the source and the load to improve the dynamic response. So finding the solution in a cost-effective manner is very challenge, and increasing efficiency and availability by decoupling dynamics of energy sources. Still very difficult to provide an independent control of active and reactive power. Due to integration of renewable energy along with the conventional power generation unit. And moreover, there must be a coupled dynamics with the distributed, distribution system and the loads through use of power electronics. So please keep in mind that whatever you works in the renewable energy, the renewable power generation unit, and apply any, dedicated control mechanism on the power converters, still finding the solution with these challenges is a great task. That is what. So you can see that as we worked very dedicatively on the grid interactive PV system, see the schematic of grid tied solar PV system. We have PV arrays. Basically, it composed of series parallel combination of a PV model. Again, PV model composed of series parallel combination of the PV cells. So we have a proper configuration to have an available DC power. This is the PV array. So as the PV array, it generates a variable DC power. So that power which is being given to the power electronics converter. So that converters including power, the power circuit as well as the control circuit, and then this will provide a power conditioning. As the PV array output is a DC power, power converters ultimately it converts unregulated DC power into controllable AC power, which is being injected into the utility grid. And at the point PCC, we connect non-linear load. That is what. So whenever we connect a non-linear load at the point of common coupling, of course, we need to satisfy the grid connection requirements, and moreover, the current which is being injected into the utility grid must be sinusoidal. So we sense the voltage and current at PCC, and we also have a grid code requirements. As I told you that the grid code requirements include independent control of active and reactive power, excellent dynamic response, good grid synchronization, and power quality improvement. So we take the the sensing parameters from the grid like active power and reactive power in terms of voltage and current, and that will be given to the controller. And in addition to that, the controller also takes care of extracting maximum possible power from the PV with the help of maximum power point tracking. So the controller, it ensures to meet all the grid connection requirements, and by generating the PWM pulses, and by activating the semiconductor switches in the power converter topology, so we are able to integrate such renewable energy sources with the utility grid. And here, as you know, that the input parameters of the PV array is basically temperature and irradiation. Basically, they are intermittent in nature, and the variation is very wide. So applying any MPPT, maximum power point tracking at the controller, to extract maximum possible power is a very very great task. That is what it means. It should be further investigated. So power converter plays an important role in controlling the power delivery, at the same time ensuring proper integration between the PV and the utility grid. So it is a very great task. And the configuration, and so I told you that the power converter is playing a major role. Mean that depends on the topology, either it is isolated or non-isolated, or maybe a single stage, or maybe a two stage, or multi-stage. So we propose a two-stage grid-tied solar PV system. It consists of DC to DC power converter and a three-phase voltage source inverter between the solar PV array and the grid. So DC to DC boost converter basically interacts with the source, and hence this is what is called a source side converter. So the source side converter basically it converts unregulated DC power into regulated DC voltage, regulated DC voltage which is being stored at the DC link capacitor. And moreover, the MPPT tracking is achieved with the help of DC to DC boost converter. So we employ MPPT by sensing the the output voltage of the PV array and output current of the PV array, and we apply a MPPT, and accordingly we generate the PWM pulse to the DC to DC boost converter. So we are able to extract maximum possible maximum possible power. And in addition to that, and the basically the PV array is designed with the small voltage and the current, so we can have a possible the maximum power. So that the low voltage, the output voltage from the PV is basically low voltage that has to be boosted up into the very high voltage that needs to again to provide an AC controllable AC voltage from the inverter. So that is what basically it boosts up the voltage from low voltage level to high voltage level. So that high voltage DC will be again inverted into controllable AC with the help of three-phase PWM voltage source inverter. So this fellow three-phase voltage source inverter is basically interacts with the utility grid at always, and hence this is what is called a grid interactive power converter. And this fellow basically integrate renewable energy, the PV with the utility grid. So the control algorithm which is being implemented at a three-phase voltage source inverter is a further investigated. It has to be very robust and adaptive in nature to satisfy all the grid connection requirements. That is what. So grid connection requirements are achieved with the help of control technique applied on three-phase voltage source inverter or three-phase grid connected PWM voltage source inverter. Please remember that, because so as we connect an unbalanced non-linear load at point of common coupling, of course there must be a problem associated with power quality. So the control technique what we employ on the three-phase voltage source inverter, it satisfy grid connection requirements. And this is the configuration of two-stage grid-tied solar PV system, and moreover it provides a DC isolation between the boost converter and the inverter. That is what we use as a DC link capacitor. So if you could see that here, for proper power flows from the renewable energy source to the utility grid, the DC link voltage capacitor, the voltage at the DC link, it has to be maintained constant. Please remember that, because the maintaining a constant DC link voltage, and you can have a proper power flow from the solar PV system to the utility grid. If there must be a problem, or if there is a voltage sag at the DC link capacitor, ultimately there is a problem of the power control from the solar PV to utility grid. That is what, at any cost, the DC link capacitor, it has to maintain the constant voltage. It has to be a controllable one. That is what we propose a two control technique on the voltage source inverter. I told you here, see that you have a DC voltage control. Basically, the voltage available at the inverter input is basically a DC voltage. So that voltage is basically an controllable DC voltage as it is basically a DC to DC boost converter output voltage, right? So the output voltage of the boost converter or the input voltage of the inverter, it remains same. So that has to be controllable, because the DC link voltage, it provides a proper power flow between the solar PV system and the utility grid, and hence there is a important information about the frequency as well. So the active power control is possible by maintaining the DC link voltage capacitor constant. So it needs a DC voltage control. As I told you that the grid connected converter can operate as a grid feeding or grid forming device.
So this can act as a grid connected converter mean if the system is connected with the grid. So grid forming converter mean still in some sense, if there is no availability, if the power which is being generated by the solar PV is enough to drive your load, so still the unbalanced non-linear load, it can, I mean, it do not receive any power from the grid, and hence the system is said to be microgrid mode. So the load either can connect power from the grid or it can power receive from the renewable energy source. It have a compatibility of both mode, what is called the microgrid as well as, I mean, the grid connected mode or isolated mode, so that this three-phase voltage source inverter can form a grid. That is what is called a grid forming device. So the main control task of the grid connected voltage source inverter is to maintain the DC link voltage constant. I told you that. So it has to be maintained constant for proper power balance between the source and the load. If there is a mismatch between supply and demand, of course, there must be changes in the frequency, and ultimately it decides the power system security. So it has to, the DC link voltage has to be maintained constant in addition to controllable AC power, which is being injected into the utility grid, what is called active and reactive power. Always it has to be controlled independently, because reactive power control is very important to maintain the voltage profile constant at point of common coupling, because it decides the power system reliability. That is what. So third option is maybe operating as a grid supporting device. So in addition to control the active and reactive power, I mean the voltage and frequency control, that grid connected inverter can also acting as a grid supporting device for voltage control, frequency control, and power quality. And whenever the grid, whenever the system has system is working with a microgrid mode, that is what. Even still, I mean, we are working on the grid supporting information, even that basically called the ancillary services. So this grid connected power converter, it also provide, I mean, ancillary services like a power quality, and also to improve the grid stability whenever there is an abnormality in the grid, you know. So the control concept, whatever we employ on the grid side converter, and it ensures grid stability when the grid is under abnormal condition. You know, very difficult to provide, I mean, that, I mean, very difficult to restore the energy when the grid is under fault condition. And hence there is a problem associated with the grid stability as well. So the power, I mean, grid connected power converter, it also ensures the grid stability when the grid is abnormal condition. So we need to have a control on the inverter, basically the AC control. So AC control means the voltage and the frequency has to be controlled. Basically, they're the AC quantity, and the input power to the inverter is basically a DC. So it should have a DC as well as AC control. So DC voltage control and AC current control. So as the parameters are, input parameters are DC, output parameters are AC. So we need to have a coordinating theory, what is called instantaneous PQ theory, as we are linearizing the parameter in terms of stationary frame alpha beta, natural reference frame ABC, and rotating reference frame DQ. And moreover, the AC power control is essential for the grid connected power converter. Either it can act as a grid feeding device, grid forming device, or maybe a grid supporting device. So ultimately, you need to have a control mechanism on both the input side as well as the output side. And this is a very important task in integrating renewable energy source with the utility grid. So this remains same for either, I mean, grid connected PV system or grid connected wind power generation system as well. So moreover, as we employ, I mean, a control technique and the voltage source inverter, still the current which is being injected into the utility grid, it must be sinusoidal rate. But it is very difficult to have a pure sinusoidal current injection, because we connects always unbalanced nonlinear load. And moreover, we uses voltage source inverter, we uses the pulse width modulation technique and with the variable switching frequency, and ultimately there is a problem associated with the distortion in the grid current. So we, I mean, certain limits, I mean, certain standards are imposing the limit on the grid current. Basically, they called harmonic limits for the PV inverters. In Europe, there is a standard called IEC 61727 international standard. IEC stands for International Electrotechnical Commission, and it includes for both steady state as well as transient condition. And we follows another important standard is from the US called IEEE 519 2014 standard. and with the title recommended practice and requirements for harmonic control in electrical power system, and there is a, I mean, still there is a, I mean, disadvantage with the IEEE 519 2014 standard, and it does not include any transient condition, and still the definition for PCC is not defined fully. That is the problem. And still in the industrial standard, I mean, for harmonic limit, still we follows IEC 61727 standard for steady state, and even small scale power generation still we uses IEEE 519 2014 standard. In addition to that, we have IEEE 1547 standard for large power sources with a capacity of 10 MVA. But moreover, whatever be the standard we follows during steady state, and the following conditions regarding the grid current harmonic content. So because as the output voltage from the inverter is basically a half symmetric, as it has a both positive as well as negative cycle, there is no existence of second order harmonics. So only odd harmonics present, basically they call the lower order and higher order harmonics up to 33rd harmonic. So there is a harmonic order between third harmonic and the ninth harmonic. It should, the distortion limit should be less than 4%. For 11th to 15th, it should be less than 2%. So as the order of the harmonic increases, still the severity is not much. That is what. So we are more concerned about to mitigate the harmonic, basically a lower order harmonic till 11th order. So we should be more concerned about third order, fifth order, seventh order, ninth order, and 11th order. So by mitigating, by suppressing third harmonic, and we are indirectly suppressing ninth harmonic. Why? Third harmonic and the ninth harmonic, basically they are cofacial. So once you reject the third harmonic, so there is no existence of ninth harmonic. So we are more concerned about fifth harmonic, seventh harmonic, and 11th harmonic. That is what you apply a control technique on the grid side converter or the pulse width modulation technique, and it has to, I mean, suppress that lower order harmonic component, so that the total harmonic distortion of the grid current should not be more than 5%. So please keep in mind that, and whatever be the control technique you propose on the grid side converter, it has to, I mean, satisfy the grid connection requirement with the total harmonic distortion of the grid current with less than 5% as per IEEE 519 2014 standard. So fails to, I mean, your control algorithm fails to satisfy the TH less than 5% means it cannot be validated in real time. It cannot be used. That is what. So this is the minimum requirement while you propose any control technique on grid side power converter. Okay. So now according to the control loop, I told you that inside, I mean, input parameters are basically a DC parameter, output parameters and AC parameter. We need to have a two cascaded loop, because I told you that the DC link voltage must be maintained constant. So you need to have an external voltage loop to control, to regulate the DC link voltage, to balance the power flow. Why? As we transfer power from photovoltaic power generation unit into utility grid via DC link. So DC link voltage, must be maintained constant to balance the power flow. So to balance the power flow means there must be a demand of active power control. So that active power control is possible with the help of a DC link voltage control. Basically, it is an external voltage loop. Okay. So the design aims for system stability with the slow dynamics. Still, you do not worry about the it should have a extremely, good dynamics. Of course, you do not. Still, you can design with the lower bandwidth. Still, the control loop, it works very fine. And another important control loop in the inner or internal loop, basically what is called the internal AC current control loop. The internal AC current control loop is very important to regulate the grid current. Why? As the inverter current is basically a grid current, right? So the inverter current has to be controllable. Why? If the grid current exceeds certain threshold value, for example, the grid current is more than the inverter output current, of course the inverter is going to be overloaded, and then it can be easily damaged unless you use any snubber circuit on the inverter. So the internal current control loop is essential to regulate the grid current and is responsible for power quality. Why? You impose a grid inner current controller so that the inverter output current or the grid current must be sinusoidal at any cost. So it is responsible for power quality issues as well. So it is responsible for power quality as well as the current protection, and moreover it is responsible for the generating the PWM pulses at sinusoidal rate. That is what. So that it inherits important attributes of harmonic compensation and the dynamics as well. So in addition to that, a variety of control, they propose another cascaded control mechanism called a DC link voltage control with inner power control instead of current loop, thereby controlling injected current into the utility grid, and still they have a direct power control. So direct power control means still you can control the output power in addition to that inner current control. So because output power control means it is an AC power control, indirectly you are controlling a DC link voltage control. So this control, it remains same as the control strategy what we propose: internal current control and external voltage control. Yes, this is the system architecture for the grid connected solar PV system and what we propose here. And this is the the DC to DC boost converter. As it receives power from the solar PV array, then it boosts up the voltage from lower value to the higher value, and that must be available at the DC link. So the DC link power is basically a regulated DC power that has to be inverted into AC. So then the AC which is being inverted or which is available at the inverter, it can be feed into the utility grid via breaker and interfacing inductor. This is what the grid interactive PV system. So this is basically a grid side converter. This is basically a source side converter. So this is responsible for maximum power point tracking. So as we sense the the PV output voltage and PV current, and we propose the MPPT technique, accordingly it generates the PWM pulses, so that will take care of the maximum power point tracking. So we sense the VPV and IPV for the input parameter, and which is being employed in the ARM Cortex M4 microcontroller to implement maximum power point tracking controller. Basically we uses incremental conductance based controller. And let's come to the voltage inverter, voltage source inverter. Basically it interacts with the utility grid, and hence it is what is called a grid interactive power converter. So it satisfies all the grid connection requirements. So we senses a load current as we connect a non-linear load, either single phase or three phase load or diode rectifier load, and we sense all three phase load current including neutral current, and we sense three phase supply voltage and three phase AC current. So we sense all the input parameters from the grid as well as from the load. Then we generate we apply a controller, adaptive control mechanism, and with the help of DSpace 1104 interfacing card, so that we are able to generate the reference current. Then reference current will be compared with the actual the supply current, so that we are able to generate the PWM pulses. So that PWM pulses, it will activate power semiconductor switches on the three-phase four-leg inverter, so that we are able to achieve desired control algorithm. So this is the system architecture. It has here the design of power circuit and control circuit is very essential thing. That is what it took almost 2-3 years to fabricate and to make a complete setup. It takes 2 to 3 years. That is a very important thing. So it's not you may think of the whatever the schematic, it's quite simple, you can easily fabricate. Absolutely it is very difficult, and moreover you should have a funding. So then accordingly you can fabricate and make a complete experimental prototype. And this is the complete design for each subsystem. Basically design a PV array, as we use the PV array with 13.5 kilowatts, so that the number of cells are connected in series and parallel for having a possible voltage and a possible current. So the maximum possible current multiplied with the number of cells in parallel, and a maximum possible voltage with the number of cells in series, so that we can have a total power of 13.5 kilowatts the PV panel. Okay, the K must be small. I am very sorry that. Okay. Then the calculation of DC link capacitor, because as the DC voltage which is being converted from the uncontrollable DC into controllable DC, that will be stored in the DC link capacitor. So the design of DC link capacitor is very essential component, as we can have the angular frequency of fundamental frequency 50 Hz. So the DC ripple is about 20% of the actual voltage, so that we are able to design a DC link capacitor about 2257 microfarad. So this design is very crucial, and moreover it should be properly designed so that the voltage can be maintained constant. And even initially this capacitor has to be charged so that it can have the constant DC link voltage of 619 volt. That is very important. So nowadays still they use as a battery bank as well as the fuel cell as a DC source for DC link capacitor. So that provide additional services to maintain the DC link voltage constant. Okay. So the determination of DC bus terminal voltage, as I told you that, as basically we apply pulse width modulation technique to invert DC into AC. So possibly you apply a pulse width modulation, the effective DC link utilization is not possible. So because if you employ a pulse width modulation, the DC link utilization is about 78.5%. It implies that you wanted to have a line to line voltage of 415 volt. Ultimately, the DC link voltage must be at least 125%. of, I mean, the line to line of 4 to 415 volt. So you need a DC link voltage of about 619 volt to invert AC with peak to peak of 415 volt. And moreover, as the inductor is interfaced on the inverter, and that is very essential to, I mean, reduces the current ripple and the, I mean, inverter output current. So it is designed with the value of 3.31 millihenry, as we assume that the, I mean, the ripple factor is about 1.2 mean 20%. So that we have designed the interfacing inductor or the coupling inductor and the inverter. And here you can have another area of research, especially the designing the coupling inductor or the filter inductor on the, I mean, on the inverter, because no inverter cannot be directly interfaced with the utility grid. There must be an interfacing inductor or the coupling inductor or the filter inductor, even with the combination of L and C or LCL with active damping or passive damping. So variety of, the filtering topology has been proposed and utilized to interface inverter with the utility grid. Just we take only the simple coupling inductor, and moreover, these also contribute for the system dynamics as well. And in addition to that, as we use the DC to DC boost converter to boost the voltage, the PV voltage into the high 690 volt. So we have taken the voltage available at MPP is about 531. So you are boosting the voltage up to 690 volt. So we have taken the duty cycle about 0.21. Even still we uses less than 0.5, but still it works very fine. And corresponding the inductance for the boost converter to boost the voltage from 539 to 690. So we have taken the the current ripple about 25%. As we uses the solar PV as an input, the input source. Of course, the variation of temperature and irradiation is very wide. So we have taken 25% of the current ripple, so that we are able to design an inductance with the value of 4.52 millihenry. And now let's come to the description of the control scheme. I told you that basically the inverter output parameter basically an AC current, voltage and AC current. So the input parameter is basically a DC voltage. So it needs both the DC voltage control and AC current control. We have an instantaneous, PQ theory to linearize all the parameters to convert the the rotating reference quantities into the stationary quantities, so that we can have possible decoupling of both active as well as reactive current component. So as we uses a Clark or Clark transformation from ABC to DQ, as ABC is basically an AC quantities, so we are transforming into DQ stationary, rotating reference frame quantities. So we uses that. So we uses the matrix, basically what is called the Clark transformation matrix, and it has a both sin theta cos theta component. So generating reference current, as we need sin theta cos theta component, basically called as unit vector templates. So that unit vector template is very important in terms of implementing the control strategy with the help of reference current generation. That is what we use as phase locked loop. And now as you have that AC quantities are transformed into DC quantities, basically it composed of average DC and oscillating AC component. So you have a ID and IQ, basically a D axis component and Q axis component. It composed of oscillating average DC and oscillating AC. So now further the ID component, basically D axis component, basically it decides an active power control. And IQ is basically a Q axis or quadrature axis component. Basically it decides reactive power control. So these both has to be decoupled. So these quantities are basically orthogonal in nature. So as again the D axis component is basically an active current component that is passed through the second order low pass filter with the cutoff frequency of 5 Hz, so that we can decompose the DC component at the active current. Now you can have ID is basically the average DC component. It composed of ID as well as ID star, so that we are able to generate the D axis component for active current control. This is the generalized DQ based control algorithm as the solar PV array with a boost converter with the MPPT, and we have a grid interactive voltage source inverter, and that inverter output is connected to the utility grid. Here the loads are connected at point of common coupling. So we have a synchronization scheme, that is what is called estimating the value of sin theta cos theta. We use the adaptive phase locked loop, and we are employing a control algorithm. I told you that control loop consists of outer voltage loop and inner current control loop. You can see that outer voltage loop, as the DC link reference voltage is set as a 690. So we are sensing an actual DC link voltage through the low pass filter, and we are finding an error between the actual DC link voltage and reference voltage, then the error is given to the control, basically what is called ID star. So the reference current generation is possible by outer voltage control loop. And in addition to that, we sense a three-phase AC current, supply current, what is called ISR, ISY, and ISB. And again, and this will be transformed into ID and IQ. So we are able to generate the reference current for both ID star as well as IQ star. So ID star is essential to control the active power via outer voltage control, and inner current control is possible with the reactive power control, what is called IQ. So and hence there is a norms of power quality with the help of reactive power, harmonic current compensation, so that you are sensing the 415 volt AC and with the actual voltages, so that the error is given to the selector switch. So during steady state condition, there is no need of any reactive power component. As the grid is working at unity power factor, IQ is assumed to be 0. So that here IQ is basically 0 mean. So during steady state, there is a norms only for active power control, whereas the reactive power control is not required, as we maintain unity power factor of the grid. So that, and this again, the DQ components are transformed into ABC with the help of power transformation. So we are able to generate the reference current ISR, ISY, and ISB. Basically, the error is basically the reference current. It is subtracted from the supply current, the actual current. So the error is given to the again hysteresis current controller as it imposes a certain threshold between the actual and reference, so that it is able to generate the PWM pulses to activate the power semiconductor switches. So we are able to achieve desired control algorithm to have an independent control of active and reactive power. This is what. And as I told you that we uses the fourth leg, basically what is called the fourth leg for neutral current compensation. When the grid is under a balanced condition, or whenever you connect a balanced load here, then ultimately the neutral current is 0. So there is no existence of neutral current during balanced condition. But whenever the system is under unbalanced, whenever a non-linear unbalanced load is connected at PCC, and there must be a problem with ISN. ISN is the algebraic sum of ISR, ISY, and ISB, and hence there must be a neutral current, so that it circulates third harmonic component. Again, there is a problem of harmonic distortion and the grid current. Okay, and this is the synchronization, as I told you that, as we need to generate the synchronizing angle, what is called the phase angle. So this phase angle has to be detected very accurately, very precisely, whenever the grid is under abnormal condition. So we have to design a phase locked loop, basically adaptive in nature. To estimate the value of fundamental, it has to forcefully reject lower order harmonics. That is, and hence what is called adaptive phase locked loop. It is like a recursive filter, and it will filter out unnecessary component which is being available on the grid current, so that it is able to detect and estimate only fundamental frequency component of 50 Hz. That is what we use a synchronous, adaptive phase locked loop here, and we are able to estimate the value of theta very accurately. And it composed of phase detector, loop filter, and voltage controlled oscillator. This is a very simple PLL, but however, as we use the compensator, basically adaptive in nature, so that we are able to estimate the value of theta very accurately. So this theta generation is very essential for controlling active and reactive power generation with the help of reference current generation. And this is the DC link voltage stabilization, as I told you that the error which is being extracted from the comparator. Basically, it compares reference voltage with actual voltage. So the reference voltage being set as 690 volt, and what would be the actual voltage, that the error is given to the error is given to the compensator, as you are designing a DC link voltage control very properly, with the optimal gain, so that it is able to control a DC link voltage very accurately, so that you are able to provide a proper power balance between the renewable energy and utility grid. So there must be a norms for frequency control. Okay, this is the characteristics of the closed loop DC link controller by comparing actual and reference voltages. And this is the concept for pole voltage regulation, as it has only the fundamental component where H is the harmonic order. So as we are more concerned about the fundamental harmonic component or the 50 Hz component, so H is assumed to be 1. So accordingly, and the pole voltage control is possible to control the active power flow. So you can see that active power flow is possible from the renewable energy, the inverter into the utility grid via interfacing inductor. And so that the reactance is a very important component that decides the overall system dynamic and also decides the active power control. So usually it has to be designed with a very low value so that you are able to extract, we are able to inject maximum possible active power from the inverter into the utility grid. So it needs an active power control that is possible by a DC bus voltage terminal. And this is the incremental inductance as we apply IC method for maximum power point tracking and the DC to DC boost converter. And as it works with the concept, the change in PV current with reference to the change in voltage, it always must be zero. During steady state, what would be the PV current and what would be the PV voltage? During transition, during change in irradiation and temperature, and what would be the value, the difference in PV current with reference to difference in PV voltage, it always must be zero, so that there is a possibility of maximum power extraction at this point. That is what the slope is zero. So the slope is always zero. So either the slope is positive if this component is less than zero, or if the component change in current with reference to voltage is greater than zero, means there is a negative slope. So always you have to hold the equation at maximum power point, mean the change in current with reference to voltage, it must be always zero. So that always the point at which we are able to extract maximum possible power is what is called a maximum power point tracking. This method, as we have taken the reference of the PV current with the reference to PV voltage, this method is what is called the incremental conductance method. This is a very classical, very cost effective method, as it needs only two sensors to sense the PV array and the PV current. But still, and I don't think so it works very fine at low irradiation, and that has to be further investigated. And this is the complete laboratory prototype of the grid connected PV system, and it composed of PV array and the DC to DC boost converter and the DC link capacitor and the voltage source inverter, three-phase four-legged inverter, and again interfacing inductor and the utility grid, and again non-linear load, and with a complete D-space, W104 interfacing card for generating the PWM pulses center. This is the complete laboratory prototype that has been fabricated. Let's come to the simulation result. As I told you that, you assume that the PV is working at a steady state. There is no changes in the temperature and irradiation. Then ultimately the pole voltage available at TCC, it remains same with a peak to peak of -339 to 339. Okay, with the peak value of 339 with multiplied by √2, right? And the grid current of the grid current, it remains sinusoidal. So at the point here, we are connecting a non-linear diode rectifier load. You can see that basically the grid current is distorted, it is not sinusoidal. So at this stage, so it means there is no active harmonic injection, there is no active harmonic current injection. So it implies that the voltage source inverter is simply an interfacing device, it does not provide any power quality improvement. So further, now the control techniques implemented here, as the your voltage source inverter, now it acting as a active power filter, so it is able to mitigate harmonics, so that it try to shape the grid current waveform remains sinusoidal. And moreover, there is a step changes in the current of 28.66 ampere. Further, there is a step decrease in the current from 28.66 ampere to 10.66 ampere. So during such situation, now the inverter is acting as a multi-purpose voltage source converter control, and again there is a control of active as well as the reactive power. And you see the the load current, it is like a staircase, because we uses three-phase diode bridge rectifier with RL that is connected at PCC, so that we are able to test the the control method for different scenarios. Without active power, without the active harmonic conduct injection, with active harmonic current injection, and with multifunctional operation. So you can see that compensating current. As I told you, during steady state and without any active harmonic filter, the compensating current is zero. As the inverter, it is acting as a harmonic current compensating device, so that you can see that it is injecting such a compensating current, so that it is try to shape your grid current waveform remains sinusoidal. And moreover, as there is a step changes in the grid current from 28.66 ampere to 10.66 ampere, and there must be a steep changes in the DC bus voltage, but still it is tried to follow the reference trajectory of 690 volt. You can see here. Okay, and further you can see that the grid current and the grid voltage, for all the cases, the grid current, it always follows the grid voltage, both are sinusoidal. Moreover, the current is follows the voltage, and hence the power factor is unity. So then the grid current is in phase with the grid voltage, and hence the power factor is unity. And moreover, you can see that the supply active power. As at the point here, the current is reduces from 28.66 to 10.66. You can see the active power is considerably reduces from 20.9 kilowatts to 13.49 kilowatts. So how you are able to maintain the DC link voltage constant? You can see according to that how the PV voltage and the PV current is getting changed. And this is the transient response, as we assume that we are connecting an unbalanced loading throughout the cycle, and you see that without active harmonic filter and with active harmonic and with multifunctional inverter. This is similar to the previous, but still we assume that the current changes from 34.37 to 15.85 ampere. You can see that how the DC link voltage stabilization is possible, as you are decreasing the current from 34 to 15.8. So ultimately there is an increase in DC link voltage. So how it is trying to stabilize and is maintaining 690 volt constant. That is the important criteria of the proposed control technique. And moreover, the grid current, it follows the grid voltage, both are in phase, and hence there is a demand of the unity power factor, so that the grid, it works very efficiently. And you can see that active and reactive power and the solar PV, solar current parameters, and moreover you can see that load neutral current. So as you are connecting a three-phase diode rectifier non-linear load, you see there is a demand of the neutral current and the load. But however, source neutral current is almost zero here, as we propose the fourth leg. So fourth leg, it will try to suppress the third harmonic current, so that there is no existence of zero harmonic current. So this is what the benefit of using fourth leg of voltage source inverter. And this is the dynamic response under solar intermittency. We assume that the solar irradiation is getting changed. So due to changes in the solar irradiation, how the dynamic behavior of the voltage source, inverter, and during state change in the irradiation, that has been examined here. And this is the experimental result for the different scenario here, as there is no active harmonic control. You can see that here the supply voltage or grid voltage remains sinusoidal, but the supply current is not sinusoidal because of what? Non-linear load is connected at PCC. So non-linear load current and supply current, it remains same. So now you go to shape your supply current waveform sinusoidal, mean you go to mitigate lower order harmonic. You can see that in the figure, you are trying to shape your the supply current waveform sinusoidal. So with the help of the control technique and what we proposes, and moreover the supply current is in phase with voltage, and hence the power factor is unity. And you can see the compensating current which is being injected by the voltage source inverter to compensate the harmonics which is being generated in the grid current. That is what here. And you can see that supply current and supply voltage both are in phase, but still the load current is staircase because of non-linear diode rectifier load connected at PCC. And moreover, as you are connecting non-linear load and unbalanced, you can see the neutral current. It is not, it is oscillating. So and hence there is a overheating of the neutral wire. Now we propose the fourth leg with the neutral current compensation. You can see that all supply current remains sinusoidal, but the neutral current, it remains zero because of fourth leg. That provides an alternate path for neutral current circulation. Okay, and here you can see that the supply current and the supply voltage are balanced and sinusoidal, and moreover in phase with the voltage. So there is a norms for power quality improvement at unity power factor. So moreover, it doesn't need any reactive power support because voltage at PCC, it remains constant. And this is the multi-purpose voltage source inverter, as it is involving the active power sharing. You can see that for all the cases, and the supply voltage and the supply current remains sinusoidal, and moreover the load current is a staircase, but still the supply current is sinusoidal. So you are able to mitigate the harmonic component generated in the grid due to nonlinear load. You can see that all the compensating current for all three phases, and for all the cases it demands supply current and the supply voltage remains sinusoidal, and moreover the THD is less than 5%. And you can see that the load current as well as the active power and what is available at the grid is about 110 watts. You can see that all the components for active harmonic filter operation. So you are able to shape your grid current waveform sinusoidal. And for all the cases, you can see that experimental result for all the cases here. This is without active harmonic filter operation. You can see the THD is about 26.5% with RMS current of 3.66 ampere, 3.366 ampere with a frequency about 50 hertz. Okay, you can see that there is an existence of lower order harmonic like fifth order, seventh order. You can observe that there is no existence of third harmonic component. Now you can see that as you are proposing an active harmonic filter operation with multi functional inverter, you can see that the THD is largely reduces from 26.5 to 4.67%, and moreover the current is the instantaneous current also reduces from 3.366 to 3.357. and still the the frequency is maintained constant. And moreover, for all multifunctional inverter operation, now the current is suddenly reduced. This is active harmonic filter operation. This is the multifunctional inverter operation. So now the current is further reduced instantaneously, so that you are able to enhance the system efficiency. In addition to the the reduction in THD from 4.67% to 4.40%, as it is injecting an active power of 1.12 kilowatts. This is the comparison table for all the three phases without active harmonic filter operation, with active harmonic filter, and with multifunctional inverter. You can see for all the cases, you can assume that you can observe that the power factor is almost unity. It's point for electrical grid is almost unity, but the load still the power factor is not unity because of inductive load which is being connected with the diode rectifier load. Okay, and this is for the transient response of the system during step changes in the non-linear load, as there is a sudden removal of load. If you sudden increase the load or sudden decrease the load, still the DC link voltage must be maintained constant. You can see throughout all the cases, the DC link voltage, it remains constant with the help of proposed control technique and the DC link. And moreover, you are maintaining the neutral current which remains constant. That is the another important thing. So how the harmonic current which is being injected, that is called the complementary current which is being injected, the response is available here, so that you are able to improve the dynamic response in terms of DC link voltage stabilization, as well as the voltage at PCC stabilization. And this is the summary of simulation as experiment. So as we have taken the correct value with the three phase RMS of 415 volt with the 50 hertz, with these the parameters of the PV as well PV panel, but still for experimental we have scaled down to 60 volt RMS with 50 hertz, as we have designed accordingly for the experimental prototype of 500 watts, because designing such system for 13.5 kilowatts is a very crucial, and moreover creating power quality in the grid is very difficult task. That is what we have scaled down the experimental prototype from 13.5 kilowatts to 500 watts. We have validated accordingly in the laboratory prototype, and this is the summary. So the multi-purpose voltage source inverter with the presented control can therefore be employed to fulfill the following approaches. First of all, to attenuate the source current harmonics introduced by non-linear load. That is a very essential, and moreover that is the norms for power quality improvement, and it is effectively serve as a neutral current compensator. As you are connecting the fourth leg, that will take care of neutral current compensation, so that you are able to neutralize the third harmonic component due to non-existence of zero harmonic. And moreover, it also contributes for the active power sharing, so that it is essentially maintain the proper power management between the renewable energy and the utility grid. And moreover, whenever there is a demand of more power from the non-linear load, still the PV can contribute the additional power in addition to the grid, so that overall power management is excellent. In addition to that, you are maintaining a DC link voltage constant, and moreover, it eliminates the need for supplementary power filtering equipment to enhance the power quality, as it doesn't have additional reactive power compensation by using any additional equipment like a capacitor or the battery bank, or maybe a D-STATCOM. Still, these voltage source inverter still acting as a factor device to inject necessary reactive power, so that voltage at the point of interconnection or point of common coupling, it remains constant. This is the another control strategy we have proposed, what is called active current control for feed forward control loop based on the control strategy. The similar thing we have proposed here, but here the voltage source inverter is shunted across the PCC, and hence this is acting as a shunt active power filter. So, but still it satisfies all the grid connection requirements, like controllable active and reactive power, and power quality improvement, and grid synchronization, excellent dynamic response. Everything is possible with the help of shunt active power filter, as the inverter is shunted across the the source, or shunted across the point of common coupling. The input power to the voltage source inverter is basically we extract from solar PV via DC to DC boost converter. The control techniques are implemented with the help of D-space interfacing card, so that the control algorithm has been has been developed in the MATLAB Simulink, and once you are running the MATLAB Simulink, it generates the PWM pulses that will be interfacing with the D-space interfacing card, so that it is able to generate the digital PWM pulses. So that will be given to digital to analog converter. Then the driver PWM pulses are given to the actual driver circuitry so that you are able to generate PWM pulses, so that you are able to achieve desired control algorithm. And this is the active current control loop with the feed forward control loop based control strategy. Here we have proposed the control technique by using only summer and integrator, so that the control technique is very simple and easy to implement in the DSpace interfacing card. And moreover, there is a computational effort. So without any complexity in the control method, we have proposed this control method. We have proposed it. We have published this paper in IEEE Transactions and Industrial Application November 2019 issue, so that you are able to generate the PWM pulses with the help of accurate generation of the reference current called IAC star, ISB star, IAC star, with the help of proposed active current control with feed forward control loop based contrology. And this is the configuration of the DSpace. And even still we can use the microcontroller or DSP. Still we are very compatible with the DSpace, so that you doesn't require any kind of assembly language to write an algorithm to implement your control strategy. Simply you develop your algorithm in the form of MATLAB simulink. You are able to generate the reference current to implement your control strategy. And this is the transient response during PV perturbation. The scenario is similar to the previous case what we have seen, and accordingly the test has been done. But here there is a DC bus voltage stabilization with the previous one and the proposed one. You can see that the red line, it indicates the feed forward control load, so that it is able to reduce the peak overshoot in addition to reducing the steady state error. This is the advantage of proposing a feed forward control loop based active current control. And moreover, this is the this is the experimental result for different case study. For all the cases, you can see that the supply current, it remains sinusoidal and it is in phase with voltage, so that there is a demand of unity power factor. And in addition to that, the grid current remains sinusoidal, and there is a neutralization of the neutral current with the help of the fourth leg. You can see that the neutral current, it becomes zero whenever non-linear unburdened load is connected. Moreover, the DC bus voltage, it remains stable, and it enhances the system stability and with good dynamic response. And this is the THD before compensation, after compensation. With the control, you can see that the THD is about 25.1%, but after the control strategy being implemented, THD is reduces to 4.7%, and the current is instantaneously reduces from 4.3 ampere to 1.66, and hence the system efficiency is increased by reducing the line losses as well. And moreover, you can see it injects only the fundamental current component without any harmonics. So this is the summary with the multifunctional inverter. Without multifunctional, with multifunctional, you can see that with multifunctional inverter and the active power which is being injected is only 60 watts. It implies that XT 83 watts is supplied by the PV, so it is contributing for the active power sharing, and the reactive power injection is reduces from 60.8 to 5.99 VAR, and hence the reactive power burden is largely reduced, and hence the power factor increases from 0.92 lagging to 0.995. Almost it is approaching unity power factor. The current reduces to 1.66 ampere with a THD of 4.7%. So ultimately, the multifunctional inverter with the proposed control strategy is able to achieve the grid connection requirements of a solar PV system with the utility grid. So summary, the proposed PV system with multifunctional inverter feeds generated real power to the utility grid while serving as an shunt active power filter. That is what. And in addition to that, the fourth leg of voltage source inverter effectively controlled to supply the neutral current, as it is compensating the third harmonic component. So, and hence there is a norms of power quality in addition to reduction in the overheating of neutral wire. The results presented here clearly illustrate that the proposed multifunctional inverter meet the THD requirement of IEEE 519/2014 standard. Please keep in mind that whatever be the control technique you proposed in the grid connected inverter system, it has to satisfy the grid connection requirement in addition to maintaining a THD of less than 5%. Okay, so thank you very much for your kind attention, and these are the key references as we could refer for finding a novelty and problem identification and the control of grid integrated solar PV system. Even you can see that the reference 3 is our research paper, as I collaboratively worked with Dr. Sabaraj Arya from SDNIT, and we have published number of research books. You can find in my profile as well. And one of the very important thing I wanted to share with you participants, that if someone is working in the area of energy storage in the design, control, and application in modern power system, including renewable energy, so you are welcome to submit your research paper to the journal Electrical Engineering by Springer. This is one of the very oldest, the journal in the electrical engineering category. Even before that IEEE is launched, this is the very oldest journal since 1910. And there is a call for papers for special issue. I am a lead editor for the journal, And moreover, I'm an associate editor of this journal, Electrical Engineering Springer. The last date of submission is 15th December, and the decision will be notified on 30th March 2021. So you can follow the online submission link in the editorial manager. You can submit your manuscript by selecting SI Energy Storage. Okay, so I hope you might have got certain idea about how to do experiments and how to develop a control algorithm for grid interactive PV system. And still, this is more in line with your ATL relevant to the electrical vehicle integration, because the concept it remains same. Whatever be the either energy source or the electrical vehicle which is being integrated with the utility grid, of course there must be a demand of reactive power. There must be a controllable voltage and the frequency. There must be a norms of power quality by sinusoidal current injection. So the connection requirements are remain same. But how the control techniques are able to achieve the grid connection requirement, that is the important task of implementing on the grid interactive power converter. Okay, thank you very much. I hope exactly I have completed my presentation. So if you have any doubt, and please let me know
that. Thank you, sir. Dear participants, if you have any doubts, you can ask, sir.
Yeah, if you have any doubt, please let me know that. So feel free and you can ask me. Definitely, I'll try to clarify your doubt. I hope all the participants are mostly pursuing PhD, or maybe someone might have done the PhD in that power electronics application in energy. So this is one of the very emerging area of research. If someone works in grid connected renewable energy systems, even photovoltaic or wind, the control techniques are very important thing, because the precisely implementing a control algorithm is very important to integrate such intermittent energy source with utility grid. Okay, so that is a very important thing, very essential in the today's situation. Yeah.
Yes. So I hope that participants are got valuable information. So thank you for a presentation, sir. And it was a nice presentation. The presentation was very neat and clean. So thank you, sir. Thank you for your presentations.
Yeah. So yeah, thank you very much once again, dear participants and dear organizing committee. It was my pleasure to share my knowledge on the grid interactive PV system. And still, participants, if you have any doubt, and please you can email me. I have mentioned my email ID on the chat box. Okay. Thank you very much. Have a nice day. Yeah.
Okay, sir.
Should I leave?
Okay, sir. Thank you, sir. Yes, sir. You can leave.